Freddy now after 45 minutes. You present your work, especially contributions.
Thank you very much. Well, good afternoon, everyone. Welcome aboard. Thank you all for coming. I'm very pleased, honored, and certainly excited to be here today to present to you my dissertation titled Data-Driven Modeling of Dynamic Movements Applied to Human Gestures on a Humanoid Robot Torso. This thesis, as Professor Rodriguez said, has been directed by Madame Christine Gallès, Professor Christine Gallès, and Professor Camilo Hernandez. And it was developed here at the SIM laboratory as the attempt to kickstart the line of research in robotics, formally speaking. Let's get started. Now, today's presentation will be, after a brief introduction, presented in three parts, three main sections, namely robot learning from demonstration, dynamic movement primitives, and role quaternions, which is the theory behind, as well as my own contribution for the method. And finally, some case studies where I have applied the method. Closing with a few final thoughts about the contributions. Now, let us start by talking about robotic manipulators, specifically rigid robotic manipulators, which were conceived as rather literally the helping hand of our industry, right? We've been manufacturing them and consuming them since the second half of the 20th century as the pursuit of the better tools to help us move forth in the industry. And after the development of technologies like artificial intelligence, especially machine learning techniques, as well as some other technologies, rising technologies of the new century, we have achieved sort of a mirroring image of ourselves with humanoid robots. And for the past 20 years, not only we have been able to develop robots like Baxter, our lovely Baxter robot acquired in 2021 for the laboratory, but also we have been pursuing robots that perhaps will go beyond our own capabilities. Now, regardless of our efforts, I find a problem in modern robotics. And the problem is that robots are clumsy. They are very clumsy, and I believe they're clumsy because of how we approach problem solving in robotics, specifically when it comes to intelligence and to movement learning, movement planning, and so on. As Abraham Maslow said, if the only tool you have is a hammer, you will treat everything as a nail. So if we continue to use the same tools, perhaps we won't go out of this valley of performance. Now, how can we make robots less clumsy? How can we make them perform much like ourselves? I believe the answer lies in teaching robots how to do things, how to perform movements for a given task, the way we would do it, in a human fashion, human-like fashion. Now, based on this premise, I have established three objectives for the thesis, namely developing a powerful data-driven movement modeling method oriented to teaching robots how to do things the way we would do them, improving this method, aiming towards model tenacity, which means models that withstand changes in external conditions. And finally, applying this method to relevant problems, specifically for the industry or perhaps for the consumer services and so on. Now, in order to tackle these objectives, I've developed three core principles, what I like to call the principles of the thesis, namely frugality, generality, and understandability. Frugality is all about how efficient we are in terms of resources, time, computational power, energy, memory. The less we use of our available resources, the better. So that frugality points towards using legacy hardware, old robots, old computers, so that we can push their limits. Generality is about how many problems within the context of movement, dynamic movement, we can solve. So the more movements we can learn, the better, and the more robots we can teach, the better. So this is where the robot agnostic concept comes into play. So basically I am pursuing a method to rule them all movements, of course. And finally, understandability, which is all about how easy it is for us not only to understand the models that are yielded by the methods, but also how easy it is for us to adapt them to new conditions, to new case studies, to new applications. Now, based on these three principles, let us explore the literature in machine learning in robotics. Now, we may divide, or it is very common to divide, machine learning in three main paradigms, if you will. So we have the unsupervised learning paradigm, which in this context we will be comprising function discovery methods, which are basically ways to let a machine from data find a pattern that describes the model that has been measured, the system that has been measured. Reinforcement learning is all about letting a machine, an agent, learn on its own within a controlled environment, and by pondering or rewarding them when they approach a valid solution from our perspective, the agents converge towards a solution for the problem. In this case, we will be talking about policy learning. And finally, supervised learning, which is, in this context, learning from demonstration, a sub-paradigm within the supervised learning paradigm, which is all about teaching robots, in this case, how we do things so that they can generalize knowledge and eventually solve the problems by applying it to new conditions, applying the solutions to new conditions. Let us explore unsupervised learning as for starters. Now, in terms of function discovery, I've chosen these three examples and I will be evaluating them rather quickly based on frugality, generality, and understandability. Koopman operator function discovery methods are based on the Koopman operator, properly, which is an infinite list, or pseudo-infinite in the real applications, list of candidate functions that may describe in a given combination the system that has been measured. Now, it requires very well-curated data to be trained, so not necessarily frugal, because, again, a lot of data and curated data is not necessarily resource efficient. It's not necessarily general, depending on how the system has been measured, but also how overfit, we may say, the model is to the data that has been measured, or the system, based on the data that has been measured from the system. And although understandable, since the models are rather analytical at the end, it does not compensate the frugality or generality. So let's perhaps go for a different option. Dynamic mode decomposition, or DMD, is basically, in simple, separating the pieces, the dynamic modes of a given measured system, so that we can identify in an abstract space how the system may be described based on the main dynamic modes. Now, again, it takes a lot of data, curated data, not necessarily out of the box, able to model from noisy data, so not frugal, not general, then again, it's only based on one instance of the system, at least the vanilla version of DMD. And although understandable, it does not compensate. So what else? SIMD, or sparse identification of nonlinear dynamics, is a method very similar to Koopman, where we take measurements from a system, a dynamical system, let's say a Lorentz tractor, for instance, and we approximate its dynamics based on a list of parsimonious functions which relate or establish relationships between the measured variables, so as to approximate the dynamics. It is not necessarily that frugal, then again, curated data, a lot of data, general, not so much, it's overfit to a given instance of the system, and finally, not necessarily compensating based on understandability. So, let's go for reinforcement learning, where we may describe methods as in two groups, or group them into simulation-based or sim-to-real reinforcement learning, where we transfer knowledge that has been found from simulations, and real-life reinforcement learning, where we just leave the robots to learn on their own within a controlled environment. Let us explore a very interesting example, the Dactyl system created by OpenAI by using a shadow hand, very expensive hardware, that after about 50 hours of training in very hefty, very cutting-edge technology, it manages to rotate a cube in space just like we would with our hands. So it's a dexterous system. It's not necessarily frugal, again, 50 hours to train. It's not general because the resulting policy is overfit to this setup. And although very performant, it's not necessarily understandable since the policies are black boxes. A lot of parameters that need additional effort to be understood and adapted to new instances of the problem. So, not necessarily our eye. We have the example of TossingBot for real-life reinforcement learning, a setup that allows a UR5 arm with a gripper to toss objects after 10,000 training steps, about 40 hours of training, and the robot is able to accurately throw about 85% of times, as to aiming for a given bin. Not only that, but it is also capable of testing the policy on new objects, different objects, with respect to those that have been used to within the learning process, regardless of their inertial nature. Again, not frugal because it took about 14 hours to train, and it was in a very hefty setup. Not too general because it is overfit to this robot, to this setup, and finally, not understandable, not necessarily understandable since the policies are black boxes. Perhaps a different method will help us. Let us try with the curiosity-driven robot, or the Curious robot, which is a four-wheel robot that is able to walk into, well, roll on its two lower limbs and use the upper limbs to throw objects or open doors. It took them about 200,000 iterations or about 1 hour in a very expensive setup for training, so not necessarily frugal, not too general because again it's overfit for this type of robot, and the policies are black boxes, so not too understandable. What else does literature have for us then? Learning from demonstration, as I mentioned, is all about teaching robots directly how to do things the way we would do them. Especially we will be exploring three methods based on dynamical systems, namely Gaussian mixture models, which is the approximation of a given data set over a set of Gaussian distributions. Very frugal, very easy to implement and for the training to take place. Rather general depending on what space the data is measured in, joint space or Cartesian space for the end effector of a robot. And very understandable, very easy to adapt, so perhaps a good candidate. Next, dynamic movement primitives, or DMP for short, a very frugal, general and understandable method based on dynamical systems, specifically a second-order dynamical system which approximates the dynamics of a given measured movement or behavior. This method is based on a forcing term. I will be talking about that later in detail, that basically embeds the movement in a dynamic movement primitive, which is what we call the method. And an improvement on DMPs is probabilistic movement primitives, or ProMP, which is again very frugal, depending on the setup, rather general, but since the probabilistic representation instead of the dynamic takes a bit more effort to adapt, not necessarily understandable, so perhaps we will be sticking with DMP for the thesis. Now, within the dynamic movement primitives literature, we find three examples of applications: joint space, latent space, and Cartesian DMPs. Joint space DMPs are the most classic DMPs application, where we measure movements within the joint space of the robot, of a given manipulator. Very frugal, very understandable, but since the kinematic chain defines the nature of the movement and there is no geometric consistency over 3D space, not necessarily general. Latent spaces, mid-ground between joint and Cartesian space, allows for merging both concepts within a manifold, an abstract manifold that represents the relationship between the kinematic chain and the end effector space. Rather frugal, not too general because, again, it still relies on a specific kinematic chain and its nature, and although very understandable, not necessarily our solution. Now, Cartesian DMPs, I believe, is the most fit option in this case, since the representation of the task are naturally over Cartesian space for the end effector to execute, represent, reconstruct the given task. So not only frugal and understandable, but also very general. What can we do to perhaps improve even more this method? Now, we may integrate it with kinematic representation, namely homogeneous transformation matrices, perhaps, which is a 4x4 matrix representing both position and orientation, which is what we call in robotics pose. From now on, every time I say pose, it will be rotation, translation, or position and orientation at the same time. They are very versatile and reliable. We've been using them for the past 60 years or so in robotics, and although they are very easy to understand and use and implement, the rotation redundancies within the rotation matrix are not necessarily fit for our purposes of frugality. Why? Well, we're dealing with 9 parameters which define only 3 degrees of freedom. What can we do about it? Well, enter dual quaternions, an 8-parameter representation of pose, position and orientation, that are not only novel and compact, but perhaps may solve the rotation Gilbert block problem, since they are based on quaternion algebra. Now, let us integrate DMP and dual quaternions to solve our problem of robot clumsiness. Dynamic movement primitives are based on a mass spring damper system, which is basically a point attractor that converges from an initial position towards a goal position, a goal value in this case, which is namely y subscript g. Now, in the context of DMP, the mass spring damper system is defined as critically damped, so the convergence is as smooth as possible. We may rewrite it this way, and by adding a forcing term and a canonical system that tunes and controls the influence of this forcing term, we may embed the dynamics of a given movement, of a given behavior, over the dynamical system. This forcing term is key to the reconstruction and the embedding of the DMPs. Now, dynamic movement primitives are parametrized by nature, since they use both the tau as the time scale factor that either slows down or speeds up the reconstruction of a system, and the scale factor that adapts the dynamics based on the initial and goal conditions. So, adaptable, parametrized adaptation. Now, in order to learn a dynamic movement primitive, we define the forcing term as a weighted sum of Gaussian kernels, defined as so, and for n Gaussian kernels, we execute based on the reconstruction of a given forcing, the approximation of a given forcing term based on data, namely y subscript d, or the demonstrated variable. We apply a locally weighted regression to obtain the set of weights, which will then define our dynamic movement primitive. Basically, the set of weights W is our DMP, our representation over an embedded space of Gaussian kernels that represents the dynamics of a given movement, of a given behavior, of a given task. This method, as I mentioned before, has been applied over the joint space, and as you may notice, although rather functional, our expectations of reconstructions are not met by the system. And this is because over joint space there is not at least in DMP, classic DMP formulations, there is no geometrical consistency. So in literature we've migrated towards Cartesian DMP, which is translation over 3D space. As you may notice, the expectation is met, so this is a very good way to represent tasks in a robot-agnostic way. So as long as the robots are capable of moving over Cartesian space, they may reconstruct our task. However, we need to represent rotation as well as translation in order for us to obtain a full pose behavior. Now, this is what quaternion DMP looks like, which is the representation of rotation over a special orthogonal space, SO3, basically the 3 axes of rotation. quaternion algebra, as I mentioned, does not suffer from gimbal lock, which is very useful in robotics. And by synchronizing these two transformation systems by using the same canonical system, we managed to encode a full pose demonstration, a full pose movement, a full pose behavior. However, this is not necessarily optimal, since the variable for the position and the variable for the orientation are independent. So what can we do about it? As I mentioned before, dual quaternions are a representation based on dual numbers and quaternions that allow to represent in a given variable, namely q bar, with a primary part and a dual part multiplied by a nilpotent, which allows for the dual number algebra to take place. Now, in order to represent pose, we choose this representation, which is the primary part representing the orientation and the dual part as half of the quaternion product between the rotation and the translation. This encodes very neatly, very efficiently a given pose. This is useful for applying rigid transformations by simply chain multiplying dual quaternions. And we may also represent kinematic chains by chaining multiplications of the dual quaternions, which represent the states of the joints within a kinematic chain. So, describing effectively the kinematic chain. These capabilities, as well as many others, allow dual quaternions to integrate neatly to dual quaternions dynamic movement primitives, or DQDMP, or base theory, that allows for learning demonstrated behaviors over special Euclidean space, SE3 space, full pose behaviors, represented as a trajectory, both position and orientation, translation and rotation. We may use the data, the measured data, to compute the error between the trajectory and the goal value, the final position and orientation of the system, the final pose, as well as C bar in the body frame, which is the twist, which is the equivalent, if you will, to linear and angular velocity at the same time. Now we compute the derivative of this twist, which is the analogous to the acceleration in both position and orientation, so basically angular and linear acceleration. And these allow us to compute the approximate forcing term. As you may notice, this is noisy data. Nevertheless, regardless, by using a canonical system as well as a set of Gaussian kernels, we are able to effectively encode the dynamics of the system, and we may use the set of weights, W, to reconstruct the full dynamics, the full behavior, extending it over time and guaranteeing convergence towards the goal value, the goal pose. This is what serves as the basis of my thesis. I've also contributed to implementing not only the geometrical coherence aspect of the method, but also the full-scale adaptability by implementing a function that adapts the forcing term towards the scale aspect in both position and orientation. And this is what I'll be using for demonstrating the effectiveness of frugal general and understandable methods over 3 case studies. Now, I've chosen handwriting as a test bed, then aim throwing, and finally obstacle avoidance oriented towards the human-robot collaboration problem, seen as a system of systems. Let us explore the handwriting task, which, as I mentioned, serves as a test bed for the method and for other methods in the context of robotic manipulation and robot dexterity. The method has been applied in DMP. Well, the method of DMP has been applied to the handwriting problem before, and as you may notice, Baxter is also capable of reproducing a given graphing, demonstrated here, barely visible, sorry, by implementing classic DMP theory. However, what if we didn't want to learn a simple lowercase a? What if we wanted to learn perhaps something more difficult like uppercase b? It may not seem that difficult. However, the initial value and the goal value being too close, so basically it being a closed grapheme, represents an issue for classic DMP. Not only that, but what if we wanted to rotate the shape, the grapheme, as to write it over a different plane of work, a workspace, a workbench, as well as scale it since the workbench is of different size? Well, according to classic DMP literature, the method not only forgets about the rotation, it should be rotated, but it also deforms and sort of skews the shape. Why is it? Well, classic DMP considers every single axis on the Cartesian space, X, Y, Z, as independent variables. There is no, as I mentioned, geometrical coherence. Koutras and Bulgari in 2020 proposed a solution for this with the global scaling and rotation framework based on DMPs. Now, it rotates, it scales, but if the initial and goal values are very similar, if not the same, the method will break. This is why in 2022 I proposed a tenacious version of this DMP method that not only is geometrically consistent, but it also avoids the overscale problem by considering the full shape as a variable within the system, so as to avoid breaking. So, hence a tenacious DMP. Now, in terms of dual quaternion dynamic movement primitives, I've chosen not only to validate it over grapheme reconstruction, handwriting reconstruction, so basically robot handwriting, but also over recognition, handwriting recognition. And by demonstrating 5 times the different lowercase a and 5 number 4s, I've managed to create this correlation matrix, very basic stuff, that regroups the graphemes, as you may notice, although not very crisply. There is some promising results over here, which point towards applications outside robot manipulation. In this case, handwriting recognition, which is something that I'll be exploring further down the line. Now, in terms of the throwing task, which is very innately human, this is something that we do all the time. We are very good at it, and we don't really realize it. We toss objects around with very good precision, but we're not very good at representing this task in analytical terms, because it is difficult, it is complex. Our bodies are complex. Regardless, I've tried to simplify it in 3 steps. The step of learning, where I teach the robot how I would toss an object, how I would throw it. The step of aiming, where the robot takes the learned primitive, the learned movement, and adapts it by aiming towards a given target. And finally, the throwing, the execution of the movement after being adapted, so that a given projectile hits a target. In terms of learning, as I mentioned, it is very easy to demonstrate by using the zero gravity mode of our lovely robot, Baxter. And the full process takes a lot less than 30 minutes. I've been very generous with this number, but this is because I've demonstrated multiple times. Not only that, but I've curated the final shape so as the dynamics to be very precise and very fit for the throwing task. So basically, finishing the movement where the velocity is optimal. In terms of adapting the method, aiming, we have 2 options. We may choose to indicate an arbitrary impact angle to the robot, so basically telling the robot how the projectile has to hit the target at which angle, and another different solution, which is the optimal throwing velocity. So regardless of the position of the target, the robot will try to find the optimal velocity so as to avoid consuming energy unnecessarily. This is the option that we'll be choosing for the demonstrations. And finally, the post-adaptation phase, which is basically rotating the plane of action that has been demonstrated about an arbitrary axis towards a plane that contains the target, the desired target, to be hit by an object. Now, in terms of throwing, after a very crude demonstration, a theoretical demonstration, I find an error of about 3 centimeters with these parameters, 100 Gaussian kernels and 20 for the critically damped variable. Now, this error may come from 3 potential sources. Integration method, because the method is based on Euler integration, very crude, very basic, so not optimal per se. Velocity convergence, since the method is not adapted to converge towards a given velocity, so it's only adapted to converge to a goal. So the velocity error trickles down or propagates towards the goal error, which then in turn propagates towards the target error. And finally, the parameter optimization. Since then again, the 100 Gaussian kernels and the 20 for the critically damped variable are arbitrarily chosen, so not optimal. Regardless, I've demonstrated the method over a simulation using a UR5 arm equipped with a spoon that holds a ball, and by aiming towards out of its workspace, so the robot can't really reach and put the ball, it has to toss it. After 100 reconstructions, 100 executions, the robot manages 95% accuracy, considering a tolerance radius of about 8.5 centimeters. This was made using the RRT star inverse kinematics planner from the movie package, and this simulation can be found online on GitHub for you to reproduce and adapt at will. Now, in terms of demonstration, on a real environment, Baxter has executed the task by aiming towards a bin, a recycling bin, and the task yields, after many repetitions, a reconstruction of about, or an accuracy of about 83%, which represents about 10 out of 12 successful throws. These numbers are not due to the method performance itself, it is mostly due to Baxter not being conceived as a robot for repeatability. Baxter is mostly conceived for human safety, so that is why it's not necessarily the most accurate reconstruction. Nevertheless, this is very on par with other methods applied to tossing and throwing objects in literature, which is very good. Now, the third case, the obstacle avoidance problem, which is based on the shared workspaces theory by Bauer and other authors in 2016, which is very simple. It's basically a human operator and a robot sharing a workspace as to collaborate in a given task. This poses safety issues for the human worker, the human operator. So, in 2019, Saber and other authors proposed the human-robot collaboration as a system of systems framework for collaboration between a human operator and a robot. This is a very interesting and promising concept, namely the awareness and intelligence layers, which are 2 systems, interdependent systems, that rely on movement planning and movement modeling and reconstruction. So we proposed in 2023 a method based on dual quaternion dynamic movement primitives for obstacle avoidance aiming towards human-robot collaboration as a system of systems. This has been also published as a conference paper. And the theory behind is based on the steering term theory on the DMP by Hoffman and other authors in 2009. This is basically avoiding a given obstacle by steering away from it based on the current velocity. We have adapted the method, the dual quaternion dynamic movement primitives method, by integrating the steering term, which is phi, a function based on the current twist in the body frame, and the obstacle pose in 3D space, represented as a dual quaternion. Again, not only position, but also orientation. So, as to demonstrate it, the robot manages to not only reconstruct a given primitive very efficiently, but it by considering a given obstacle, the robot manages to steer away from it and at the same time try its best to keep and reconstruct the dynamics as best as it can whilst steering away from the obstacle. And this is compatible with the theoretical demo, where we give in the dotted line a demonstration, and by considering the ball, the red ball, as an obstacle, the robot, or well, in this case just the reconstruction, successfully steers away from the obstacle. And this is very interesting for, again, the human-robot collaboration aspect of given processes in the industry, namely processes where safety has to be very tight in terms of robotic systems. And by considering a static obstacle as the critical point, a critical head point, for instance, the dynamic movement primitives are effectively adapted to these contexts. So, as to recap our results, my results, I've managed to deliver a tenacious DMP formulation, not only for handwriting reconstruction, but also for potentially handwriting recognition. The first one being published in 2022. The second contribution, or the second result that I've provided, is a throwing dual quaternion dynamic movement primitive based on two dual quaternion aiming solutions. This is to be eventually published. It is in an ongoing reviewing process. And finally, the static obstacle avoidance dual quaternion dynamic movement primitive method aimed towards human-robot collaboration as a system of systems. Well, again, published in 2023. Now, as to conclude the presentation, you'd call it. Sorry for that. So yeah, I've managed to develop a tenacious dynamic movement primitive method. In this case, within the context of dynamic movement modeling. I've also managed to propose the three core principles behind the thesis, which I haven't met at its integrality in literature: frugality, generality, and understandability, which show to be very interesting for research. And finally, the implementation and validation of the method over three different robotic manipulation cases, which are effectively very interesting not only for research but also for the industry. Now, these results have their pros and cons. In terms of pros, they are compliant under the principles, the three principles of frugality, generality, and understandability. The method is frugal, general, and understandable. It is highly flexible and versatile, as shown by the three applications, and the results are effective, being on par with existing literature. But the method is not perfect, sadly. It is not standalone. It relies on third-party and external modules, such as inverse kinematics, for instance. It is of niche applicability, so sadly not a future substitute of PPO or so proximal policy optimization, or perhaps LLMs as of today. And it is yet to be optimized for the industry, since at this point the model or the method is not ready for consumption. So I would not just simply deliver my code to a company for them to apply it, but the principles behind as well as the theory are very promising. So as to continue with the research, I propose to enhance the tenacity of the method, mathematically speaking, by including new and different terms, or by improving the current capabilities. So, for instance, improving the kernel optimization, as well as the parameter choice, or the choice of parameters. Optimizing the code deployment, since all of these demonstrations were deployed by using, through Python code, which is interpreted, and it is certain that by migrating over C++ or any other compiled language, it would be efficient, more efficient. Then we have the integration of a robust framework, which is not showing, there you go, that considers perhaps the given set of primitives, so a library of primitives and movements, as well as movement planning and many other interesting characteristics for the industry. Harness the dual quaternion-based inverse kinematics power, which is currently being explored in literature and is very interesting for this kind of theory. We have the development of the rhythmic variation of the dual quaternion dynamic movement primitives, which would be interesting for consumer applications such as cleaning surfaces or sweeping the floor or even kneading bread. So repetitive movements or tasks. And exploring further research paths such as the choice of dynamics over kinematics. So since the currently version of the method is dual quaternion based, but dual quaternions expressing kinematic data, it could be ported eventually over dynamics, as instead of using the twist, using the wrench. Parameter optimization, which is a very interesting subject to tackle eventually, so as to how to properly choose automatically the number of quotient kernels, for instance, or the parameters that define the model. And finally, a latent space hybrid, which will integrate the kinematic data over Cartesian space with a latent space representation of the robot kinematics, which would effectively enhance the efficiency and the performance overall of the method. Now, as a closing thought, I would like to invite you all, as well as myself, to think about robots as the tools of the future and the tools of today. Not as a replacement for the human hand, but as an enhancement of our capabilities. So, in order to guarantee the synergy between humans and robots, I propose to focus in making robots more human in nature to guarantee a more human future. This has been my presentation about a frugal, general, and understandable dynamic movement modeling method, namely dual quaternion dynamic movement primitives. Thank you all for coming. I will be answering to your questions.
Thank you very much.
Thank you.
Presentation. We will start a session of the questions. I'm going to start with the viewers. Okay.
I apologize for the delay. Apparently my computer is not handling very well both streaming and the presentation. I'm sorry.
So we start with the first reviewer, so Professor Gunderman from the University of College of London.
Brilliant, thank you very much. Thank you for the presentation and giving an overview also of the work that you have been doing over the last few years. I would like to have, first of all, your perspective and opinion about the advancement in robotics. So you started with the humanoid robot,
Yes.
and then you mentioned that there are humanoid robotics coming in. You can, of course, look at humanoid robots from the early 1920s, 1930s, which is before the Unimate actually came, and go along that history, trace history, and then you have the universal robots, the Franca-Amica collaborative robots, etc. And you can also see that as a separate stream on humanoid robots. So what is the most crucial advancements in these streams in terms of robotics history, in your opinion?
Yeah, thank you. Well, I would say in recent years, the most crucial advancement has been the actuator development. So, for instance, Boston Dynamics has been relying on, for the past decade, on hydraulics. And they recently have migrated towards all electric, an all electric humanoid, for instance, which is very interesting. That wouldn't be the only important advancement lately. There is soft robotics, which I believe you are very fond of. There are many new technologies within that context, especially materials, which have improved and allowed for new developments. But in the context of humanoids, I would say there would be the actuator landscape, as well as the novel techniques such as this one, that allow for a broader landscape of how to tackle problems.
Okay, and within actuators, what do you think as the breakthrough of the last few years?
Yeah, so I would say that's rather opinionated. In my case, I would say like brushless DC with like powerful brushless DC motors. But in the context of collaborative robots, I would say, although not many people agree, that the actuators within robots like Buster, which are mechanically disadvantages, if you will, not fit for repeatability, but very safe to use in the collaborative aspect. Those would be like my highlight of the actuator landscape. Yeah.
So then, maybe not so much in your presentation, but in your thesis, you mentioned that artificial intelligence is there to power these machines in the future. So you clearly see AI as an enabler for robotics. So you can also see that from a different angle and say that robotics is the enabler for AI to show impact. What is your opinion about that?
That is a very interesting play on words on the argument, and since I would say it's more of a virtuous cycle. So the development of AI enables the development of robotics, which in turn pushes through and advances AI and so on.
And why do you think this might be my opinion? Why can this push AI? I think it was very nicely in your thesis as well.
Oh yeah, it's about motivation. So pursuing solutions, force or pushes a given field. In this case, since the movement intelligence is within all over the thesis, it motivates the development of, in this case, AI.
Okay. So I like this very much because this phrase very much because you showed also the challenges not to only learn in simulation but also in the real world. I think you had examples of reinforcement learning for real world environments, and because these real world environments are changing continuously, you actually have dynamic data which might help machine learning techniques to improve. So that leads me up to your contribution. And in your thesis title says, data-driven modeling of dynamic movements applied to human gestures on a humanoid robot torso. Yeah. At the same time, you clearly define your KPIs. One of the KPIs, so the key performance indicator, being generalization. But in your title, which I think is also very much linked to the contribution, you clearly state on a humanoid robot torso. So can you comment a little bit on, your contribution, which you say is generalization of modeling, but at the same time you roll back when it comes to your title?
Yeah, so it was a very odd choice of mine, I admit it, but because of the strength of the demonstrations over the Baxter robot, which again for me is an icon of the frugality aspect as well. So Baxter is not the best or most performant robot in the market. So my objective originally was to push the frugality aspect, and in the midst of the thesis I found the generality aspect to be very interesting. So that's why, for instance, in the throwing experiment I simulate over robot arm, a UR arm, which is different from the robot. So my contribution in the generality aspect would be the robot agnostic aspect of the method, although it is not clearly stated in the title.
Okay. So may I ask then, so you showed some of the simulations done with the UR robot,
Yeah.
universal robot. So how much platform agnostic is your modeling?
Well, in principle, very much robot agnostic. Now, it requires, certainly, given manual adaptation. So I cannot simply deliver the model from this one right away to the next robot if the initial and goal conditions or poses are not reachable by the two robots. But by adapting it, so by shrinking the space, for instance, which is very easily achievable thanks to the scale term that I developed, it is very robot agnostic. So yeah.
What needs to be changed, adapted in order to make it robot agnostic? So you have to have a robot that has a similar workspace. Okay, let's say the throwing task, and that particular case study is the same. What else needs to be retraining?
Yeah, so basically it would be the initial and the goal position, the initial and the goal poses, effectively. Then the execution would be need for both.
So if you have a 4 degree of freedom robotic arm, it is also...
That is a very interesting point. It has to be a full 6 degree of freedom in order to reproduce the whole space of represented by dual quaternions, which is the SE3 space. Yeah.
So that leads me also to a further question about your key performance indicators and the measurement. In your presentation, you demonstrated a very qualitative measurement of frugality, generality, or how to generalize it, and understandability. So if you are introducing this concept as the 3 principles, how can I, if I have a model, how can I quantitatively say that I compare to what you have achieved?
Yeah, so in terms of frugality, I've evaluated it based on how much time it takes, walk time it takes to train a model, how much memory the model occupies, although I have not made very precise measurements on that. And finally, how, in terms of the robot, how much energy, quote unquote, has been consumed. Not electric energy, but more about how much effort the robot makes by executing a movement. Well, in the case of reinforcement learning techniques, executing the policy. But yeah, so those would be in terms of frugality. In terms of generality, as I stated, what varieties of movements can be modeled through the method. I demonstrated over a planar task, which is the handwriting task, as well as 3D full range of motion tasks. So there is one aspect of generality. The second one would be how many robots. In this case, as many robots as the robots that can reproduce a full 3D space task. So both position and orientation, full 6 degree of freedom. Finally, the understandability. It is rather qualitative in terms of how to evaluate it. I mean, I wouldn't know how to state which methods to use in order to define how understandable a method is, beyond how I find them understandable in terms of how to adapt them and how to tweak the parameters. So in terms of, for instance, automatically learned policies, learn from like reinforcement policies. As I mentioned, there are black boxes, and when we look at them, even graphically, they are very abstract. So there is an additional effort, and that renders it less understandable right away compared to these models, which are wage matrices.
So all these learning algorithms, or machine learning and reinforcement and supervised learning algorithm could be ignored from the very beginning because they are not understandable.
Well, the reinforcement learning ones, perhaps, yeah. but I wouldn't say that the unsupervised learning, especially function discovery algorithms, would, since the output models are, analytically speaking, very clear. So the relationships between the variables and the desired outcome is very clear. So that's why they rank up in the understandability.
Yeah. So that raises a question. In the first place, why did you not look into physics-based models? In the end, you have a robot here, and let's say 6-degree of freedom robots in general are made out of rigid links and joints. They are very understandable. In some cases, they might be computationally very effective. Of course, you can argue that you cannot generalize it, but I mean, you're just arguing that, okay, there has to be some assumptions to be made in order to make it generalizable. So,
Yeah.
what is your, what are your thoughts on that?
Yeah, so the order in which I present the three paradigms is the order at which I looked from the get-go to literature. So physics-based function discovery, namely SIMD and DMD, were our first options. So that's why I would say defines the pathway that I've laid in the presentation. Then I went to look for reinforcement learning methods, which seemed to be very performant, and they are, but the hardware limitations, namely the equipment used to train models, like they use very expensive equipment to train them, lowers them in the frugality aspect. So that made me think, oh, perhaps there are other solutions. Enter DMP. So yeah.
So then, with your three use cases, why did you choose specifically those ones?
Well, they were not only interesting for the validation, like the handwriting as a test bed, as I mentioned, but they were also very, how would I say it properly, eye-catching, perhaps, especially the throwing task, since it's very dynamic, and it seems to, when reproduced, it seems very human, very natural. And the third case, it was chosen because of how applicable it is for the industry. Mm-hmm. So those will be like the drivers for the choices.
Yeah. How did you do actually? So you showed a video of the training. Was that an actual video of the training?
Yeah, same.
Okay.
Absolutely.
So how? So when you throw something, it also matters when you release the object. So when you are showing training the robotic arm, how did you make sure that you also teach when to release the object?
Right. So not only I had the buttons in the arm, because it is equipped with buttons to interact with the robot, configured to indicate where, from my experience, the ball will be released, but also within the 30 minutes or so of training, I curated the movement so as to the goal value, the goal pose, the point of release, would be the last value. So the maximum velocity as the point of release, and the nature of the movement will take care of the rest of the movement. So the moment where I release it is when I get to the goal pose, and then I release and I continue to reconstruct after the action of the forcing term. So the convergence towards the pose is achieved. So basically, I believe I described it in my case study within the thesis. So yeah, that would be it. Yeah.
I have one more question regarding the success rate.
Yeah.
You showed one of the examples, I think that was picking and throwing, which achieved about 70-80% success rate.
It would be the simulated one, perhaps?
No, I think that was in the real environment. With the
Oh yeah, so tossing bot. Yeah, the 85% of accuracy. Yeah.
My argument would be that some of this is also due to the fact of the intelligence embedded in the hardware.
Oh yeah.
So you have, I think, a suction cup.
Can you again?
Only a suction cup and effector, for instance.
I don't. I just have grippers, but over there. Yeah. Yeah.
So when we look at the success rates in your three applications that you showed, how much would you argue could be compensated by more intelligent hardware, so what we then call embodied intelligence?
Oh, a lot, yeah. It would be highly compensated if we were to implement more mindful layers of intelligence, like hardware intelligence, as you mentioned. Absolutely. So one of the mottos, sort of the thesis, has been to there's no way but up from here, because this performance is based on the rawest implementation possible. So interpret language, barely touching the inverse kinematics service because it's out of the box, and so on. So just for instance, mindfully applying the inverse kinematics so that it considers the full movement from the get-go, for instance, would improve it. Using a suction cup as well, and so on. So yeah, it comes as well to the simulation, where you see I call it passive handling, because there is no gripper, it's just a spoon. It will also increase by using a gripper. So yeah, absolutely.
Thank you very much.
Thank you.
Thank you. So next speaker will be the second reviewer. So he's Carlo.
Thank you, Freddy, for the presentation. It was very clear, I think. So you gave the right overview of what you have done. Also, the thesis work was, in my opinion, good, because, I would say robust, because you developed methodologies and also tested them in real practical situations, which is always a nice test.
Thank you.
So my evaluation of the work is positive. I have a few questions. Some of them were written already in the report, so it's
yes.
Well, at the beginning, I don't completely agree with the classification you did at the beginning between reinforcement learning, supervised learning, and unsupervised learning, because supervised and unsupervised learning, typically you learn a model of the system, okay? In reinforcement learning, you don't learn a model, but you learn a controller. So they cannot be compared because they have different goals. So it's, can you give some comment and explain why you did this kind of classification?
Absolutely, yeah. So this is a very opinionated subject, in fact. In literature we find a variety of uses for the classification within the AI realm, especially machine learning. Now, I've chosen to lie within this spectrum of the learning from demonstration as well as the function discovery, so as to justify the ways of working of the two different approaches. In terms of reinforcement learning, they would lie within this spectrum where they overlap with supervised learning and unsupervised learning in terms of the applicability. So, in short, basically I chose to classify them in this way so as to focus on the results and not on the way that I use, so my path towards the result, basically. In terms of policies, for instance. Policies cover the whole control chain. Whereas in this case, we're working with, in the context of functional discovery, with models, and in the context of learning from demonstration, with models as well, but model approximations. So, in short, I've chosen this classification based on the functionality and on the answer to the question, and instead of the mathematical nature of the answer. So yeah, I don't know if perhaps that.
I understand. Probably this is a classification made in the machine learning field. Yeah. While in the automatic control field.
I understand.
Yeah.
So it's again, it's very opinionated.
I understand that this is. Okay. So another thing, again, was in the report. So basically, you learn the force or the torque or together, both of them, that you need to obtain a given trajectory. Okay. So when you do the series with the kernels, you learn basically the input of the system that is supposed to generate the given, the desired trajectory.
Yes.
And you learn this from data. That is okay. But then you apply the force in open loop. This is again a question from the point of view of automatic control. So you apply the force in open loop. Is this correct? And can this give problems? Because we know that closed loop is better because you can reduce disturbances, uncertainties, react to possible disturbances and uncertainties and so on. So, if you want to comment on this.
Sure. No, I absolutely agree. Now, the thing with DMPs, as we apply them, is that originally they were conceived as a motor control policy, right? So they were learned and applied as perhaps open loop, or by implementing these equations based on original theory, they can be applied as a closed loop control module. Now, we're using the theory as you mentioned, model the input to the actual system, so the actual execution, torque, and so on. We do not get involved into the control module. We only touch the movement planning, if you will, or movement generation module. And the motor control for Baxter, for instance, is this chain, this chain of blocks. Now, it is possible, I agree, to mitigate uncertainty and improve performance by eventually, perhaps, including the whole chain within the control loop. I agree. The thing is, the control aspect of the implementation fell out of the scope of the thesis, especially because the theory is rather new. So
I think your approach can be adapted to this setting. So
absolutely.
You can bring it and use it for this setting also. So
absolutely, yeah. I agree.
Okay, sorry if I interrupt.
No, not true. But yeah, I agree. This would absolutely increase the performance of the method. And as I mentioned before, there's no way but upwards from here. So yeah, absolutely. I don't know if that answers to your question.
Yeah, I think it answers. You can
Perfect.
also, so it is related to one previous comment. So you can combine this kind of data-driven learning with physical modeling in this way. So it's so you can get the best from both approaches.
Absolutely.
And okay, another thing that I would like to ask you some more details about the case where you have an obstacle or more obstacles. So if you can give more details on how you treat this situation.
In details in terms of anything in particular?
More mathematical.
Oh yeah. So let me go back then to the previous one. But yeah, so as I mentioned, it is based on a steering term, which is also at the same time based on potential field theory applied to obstacle avoidance. So it's basically taking the obstacle as the contrary, the opposite to an attractor, so a repellent, if you will. So the actual point or our position, our orientation as well in the manifold of rotations would be steer away from the obstacle. I did not prepare a slide about the actual theory behind, but it's basically an equation that takes the cross product in both position and orientation tangent spaces from the obstacle to the velocity, so as to obtain the steering away from the...
So then what you apply to the real robot is the sum of the two. So you apply f plus phi.
Yes, absolutely. Yeah.
Okay, so phi suppose that you know everything about the obstacle, so position.
Yeah, it's an assumption. Yes.
So on.
We didn't delve into instrumentation so as to detect an obstacle in real life, for instance.
Okay, but this is another problem.
Yeah.
If you have more obstacles, well, you put the sum of different.
Exactly, absolutely. Now, the only caveat with this application is that this steering term is defined for a static obstacle. It can be improved for a dynamic obstacle eventually.
It becomes more complicated because we have also predict what is. Yeah,
Precisely.
okay.
And you can use like model predictive control, back in the chain, and so on.
Problem that,
Yeah.
You can treat in the future.
Absolutely.
Okay, another question, it's a more technical one, about the Gaussian kernels that you
Yes.
used. So, well, about the choice of the parameters, you already partially gave some indication, so it's future work to
Yeah.
develop a method for choosing the parameters. But I guess here you just did some kind of manual tuning or heuristic tuning,
Yeah.
or for example the centers, and because you have to
Oh yeah.
the centers and the width of the.
Absolutely. So there is an analytical definition, heuristic based, for
Okay.
the centers and for the widths. Absolutely. And it is very well documented in literature. I've chosen the most basic bare bones one, so as to simplify the method to guarantee frugality. But there have been proposed, and I believe I've mentioned it in the thesis, different approaches for choosing the Gaussian kernels, and not only Gaussian kernels but modifiers and Westland functions, I believe, as well. There are also applications of the DMP, like DMP plus or plus plus, where they use Gaussian kernels truncated and biased, so as to prioritize a given section of the movement to give it more resolution, for instance, and so on. So yeah.
I don't remember if you did some comparison between different possible choices of the kernel.
Well, I didn't do them.
Just on this and.
Yeah, so I didn't do them myself, but
Okay.
they are already reported in literature. And although very interesting results arise from different choices besides the classic Gaussian kernels, the difference is not significant at this scale, so 100 and so on.
According to my experience, you can use different types and then you get similar results because they work all the same way, more or less.
And the same thing happens with the canonical system. So there are people that have used different canonical systems for both phasing and gating, so as to shut down the system and to synchronize it and so on.
Because they could also tell you to use neural networks to.
Absolutely.
But probably kernels are better.
And I believe
for
it has.
For this goal, yeah.
Yeah, no, I believe it has been done already. Colbert and other authors in 2009 or 12, something like that, they did a merging between classic DMP and reinforcement learning to tune what they call meta parameters, which is basically how many Gaussian kernels, what is the critically damped choice of parameters, and so on.
Mm-hmm.
Yeah.
Okay. I have one last question about the robot that writes the letters.
Yeah.
Slide 18. Maybe.
Perhaps this one. Oh, sorry, let me go back. So I can show it, yeah.
So yeah, basically, just to understand the process from the beginning to the end. So you generate some. So there is a human that writes the letter, that generates the data,
Yes.
and then you use the data to identify, let's say, the model, and then the model is given to the robot that reproduces. And so you have to, for example, if you have 21 or 23 letters, you have to construct a database with all the letters. So for any movement, you have one set of data, and then you have to build this database depending on the set of movements that you need to.
That is correct. Yeah. So there's also work being done in the handwriting context in DMP. Namely, there is not this one, but there is a parallel paper from different authors that deals with library building, and I believe it's older. So you build a library not only for each grapheme, each letter, but also you may build a library for each one independently. So many different A's, many different B's, and so on. Yeah, and daisy chaining them is a different problem in DMP. So basically joining different primitives so as to write a full word, for instance. Yeah.
And well, it depends on what the robot has to do, but maybe you have problems of memory. Okay, you can put a lot of letters and other trajectories, so...
Yeah. So that is why I put in perspectives like the building of a framework based on DMP, so as to solve more complex problems like the full handwriting spectrum, if you will. Yeah, absolutely.
Okay, but future one.
Yeah, totally. It really fell out of the scope, sadly. But the full handwriting test bit, as is, would be very interesting to explore with a library, a full library, and finding a quantitative way to evaluate the reconstructions. Because as of today, there is no objective quantitative KPI to evaluate how correct the handwriting is being reconstructed. So yeah.
Okay. Thank you.
Thank you.
This was my last question.
Okay, thank you very much, Pablo. So now, before allowing the supervisors to speak, I'm going to ask some questions,
Sure.
some comments. So first of all, I want to congratulate you for your work.
Thank you so much.
To read the manuscript. I think that the manuscript was very good writing. I find that very good people. So it was very easy to read and it was a very good work.
Thanks.
So the manuscript was very good.
Thank you very much.
The second point, I think that it's very interesting the work that we have done. I mean, in the sense that I really like the idea of try to find some analytical studies about how to code information of the movement. So it's instead of having a black box. So it's something that personally I like very much. So I have anyway some questions about the work.
Sure.
So the first question is about so the first contribution. So it was in the handwriting task. So as I understood, so you modify the dual quaternion DLP. So in order to be able to make better so the process of reproducing some letters or scanning some information that we have. So how was the process of finding these results? I mean, you make several tests and there are things that doesn't work, this didn't work, or how was this? Can you explain a little bit?
Absolutely. So originally I developed a tenacious version of the classic formulation with by including the geometrically consistent rotation and scale, global scaling and rotation theory. And I noticed it wasn't as efficient as it could be, since the two independent models would not be intrinsically related in space, so I couldn't do handwriting recognition as I would like it. So recognizing not only the trajectory, but also how the hand moves in how it rotates. So that's when I migrated to dual quaternions in that context. Then I noticed that the recognition wasn't crisp enough because the scales, the dynamic scale was not matching, and that is because there was a term missing in the new dual quaternion DMP formulation. That is when I proposed the scaling equation, the scaling function, which solves the problem, but yielded more interesting results for handwriting recognition. But yeah, so the whole chain was functional, but I noticed like sort of pet peeves, if you will, very tiny details that could be improved, and each detail led me to a new improved version.
Okay.
Basically, yeah.
So I have another question about so you say that so you take the position, you learn the position, you learn from the data of the position, and using the position you are calculating the speed and the acceleration.
Yes.
So I suppose that in this processing you have some noise because.
Absolutely.
And after you are using this acceleration and this speed to calculating the force, that theoretical force that you are using to evaluate the weighting factors of the causal function.
Yes.
So you say in the manuscript that there is no influence of this noise of in the So I read something about that.
Yeah.
Say, okay, the influence of the noise is not very important. I understood. Why?
Yeah, so it is, as far as I understand, given by the nature of the embedding. So the Gaussian kernel distribution approximated by using locally weighted regressions, approximate to a range of points around the given Gaussian, right? So in this way, it suppresses quite effectively the noise, since it conserves the underlying information beyond the noise, which is again approximated through LWR. So that's why I would say it is not like the influence of the noise is not that important, at least from my experience. However, there have been at least 2 studies that I may remember about how effective DMP is at embedding the dynamics of a given movement or system or whatever, if measured as a noisy measurement. And again, they come to more or less the same conclusion. So the noise does not influence the actual embedding as long as the noise is not bigger than the actual dynamics. So yeah.
Okay. So, okay. And do you think that it's possible to, once you have the position, have analytical calculation of the speed and the acceleration?
Come again? Sorry?
If you have when you are, for example, you are training in the throwing task.
Yeah.
You are training the robot in order to learn the trajectory that you want.
Yeah.
So I suppose that after several training, you have a mean trajectory that you want to follow.
It can be done, yeah.
And so do you think that it's possible, instead of calculating the speed and the acceleration that numerically from this trajectory,
Okay.
doing this analytically, this calculation in order to after delivering with analytical?
Yeah, so not only I believe it's possible, it has also been demonstrated in literature. However, the most bare bone implementation of DMP is always numerically computed, since it does not require a battery of instruments to measure the movement, so only instruments that detect the position of the end effector. So yeah, it's possible, but I chose the most simple approach.
Okay.
Yeah.
Okay, so another question of the human-robot collaboration. So when I start reading this part, I was expected to see some same trajectory with the human and the robot. So
Yeah.
and I see that was in fact the collision avoidance, more or less. So my question is, do you think that it's possible to adapt the dual quaternion NP to have a common trajectory with human?
A common trajectory as in shared with a human?
Yeah, instead of having, because now you are doing the collision is avoided because in your procedure you are putting a point that's generating a repulsion
Yeah.
force of something for the trajectory, doing other way in order to have to be able to have the same trajectory as human for a while.
Yeah. So I believe you've worked in multiple manipulation or collaborative manipulation before. So different approaches, of course. In this context, I believe it has been done, but not in the context of a human-robot collaboration, but in multi-robot manipulation. So different agents sharing, let's say, moving a big bar amongst the two robots or multiple robots. It can be adapted, I believe, to human-robot manipulation, like co-manipulation, but I think it would be more involved in terms of predicting the behavior of the human. So perhaps other methods are more performance in this context. I remember Professor Lynch, Kevin Lynch, has worked as well in from Northwestern University, has worked as well in multi-robot and robot-human human-robot collaboration, manipulation or co-manipulation, and I believe his methods are based on variable impedance. So I believe that will be more fitting for that specific application. So in the context of human-robot collaboration as a system of systems, that module would be handled by a different dynamic system or method, and the method which avoids humans or as to guarantee safety would be the DQDMP, for instance. So yeah, perhaps integrating multiple models within the same system of a system of systems aimed towards human-robot collaboration could be a more fitting answer.
Okay. Have you done the experimental results with the collision avoidance with the human robot?
As of today, I have not, and it's due to the measurements of the robot as to avoid an object. I believe at the time it was too finicky to set up, so I put it aside. But it would be interesting to explore to further enhance the performance of the method, especially replacing the steering term for a dynamic obstacle steering term, so that I can not only put an object so that the robot avoids it, but actually moving the object so that the robot avoids it actively. Yeah.
Okay, so finally I have another question related with a question of,
Sure.
of Carlo. So you show a diagram, so a block diagram with the inverse kinematic, etc. So it's something that is
Yes.
from the control point of view. Not this one, but use the one before in the way that you show that the way that you are doing the implementation of all the things. So I understood it's not this exactly this closed loop, no? Because as you are doing,
Oh yeah.
this is the perspective, no? It is one. So
Yes.
here you have your DNP. So the output of the DNP. What do you have from the output of the DNP there?
Oh yeah. So the output of the DMP is the end effector pose or the end effector trajectory
Is the
over time
in the trajectory and orientation
in the workspace. Yeah.
After you have the inverse module that produce that in the position of the articulations.
Yes.
Okay? And after you have a position control in the okay.
Which I don't handle, but yeah.
You don't have, so you have some, and I read you mentioned a little bit in the manuscript that you have some problems with the inverse kinematic. So it means that so my question is, you mentioned that in the throwing task. So is in this task in which you have more problems in this inverse kinematic.
Oh yeah, but it was very specific. Yeah. So the problems were related to how the MoveIt package handles inverse kinematics for a given problem, for a given trajectory, as well as the different planners. So in the demonstration I used, I believe it was the RT star. So the RT star. But in the thesis, I believe you might have seen a table that compares different planners to execute the task. But yeah, so the problems are out of my control, more or less. I could delve into the granular details of the package, or I can simply develop my own inverse kinematics. So, well, yeah, it's an additional, an additional error layer, if you will. It is not due to, the error is not due to, or the accuracy is not due to the method itself, because again, it would technically be 100% accurate all the time, falling into the same point in space or hitting the target, but since the granularity of the execution is not handled by myself, but by the method, yeah.
Okay, so thank you very much.
Thank you.
From my side. So I'm going to now, Camilo, you have comments?
Maybe few. Before I give my comments, I want to thank the members of the jury for the reviewing work. That's very nice from you. Now I want to congratulate Freddy. I found
Thanks.
the presentation fantastic. I'm very proud of this presentation. The way you presented was very nice, to my opinion. So, congratulations.
Thanks.
Just to complement a little bit about the conclusions and perspectives, I think there is a research possibility afterwards in including hyperdual quaternions in the method. Since right now we are dealing with the poles, like the orientation and the position of the end effector, but by implementing hyperdual quaternions we can add two variables more, which is the velocity and the angular velocity of the movement.
Yeah.
And I think that can add
Absolutely.
add to the method.
I absolutely agree. And even migrating to hyperdual quaternions and dynamics, we could represent the twist, representing the whole, instead of the twist, the wrench, which would be effectively dynamic information embedded as well as the trajectory. So yeah, absolutely.
As for the rest, I don't have any questions since I work with you side by
You know
side.
already.
I don't have tricky questions.
Well, thank you.
Yeah, it's all for my
Okay, thank you very much.
Thank you.
So Christine?
Thank you, Mr. President. So thank you, as Camille said, thank you to all of you, and especially the members of the Illumination Board coming from far away and for reviewing the work of Freddy. Thank you for your time. I hope I will have enough voice until the end of the session. I won't ask you any question as well.
Thank you.
In fact, Camille was in the front line to supervise your work. I try to do my best to help you and to follow your path during these studies. As the head of the master you joined 5 years ago, I'm very pleased to see your path during these years with us, during the master first and then at the lab. And you had also to overcome the pandemic period where it was not so easy coming from another country. So when you arrived in France, you did not speak French, if I remember.
At all, yeah.
And so I think you made an impressive parcours path.
Thank you. Thank you very much.
In our country, and it's congratulations for all your work and your integration, all you have done during these years.
No, thank you very much. I'm really pleased. I'm grateful with both of you, and as well to I'm grateful and pleased to you, members of the jury, to coming here, examiners, and also the director. Thank you all for coming here today.
So that will be all from my side.
Okay, thank you very much. So
Thank you.
so now I want to move to another place.
Yes, we are going to the meeting room just over there, and we will meet you at the lab when
All
we
right.
are finished, so you can close the system.
Absolutely.
And we will meet at Maison Aimée 80
Sure.
when we have finished.
All right. Well, thank you again, and see you in a bit.